welcome to the lecture number 28. So, today we are going to start with the gravity gradient satellite. So, what is the basic principle involved here? See, we start with one very simple representation. Say this is the orbit of the satellite. And here say earth is present. Center of the earth, let us represent this by O prime. And we will take one very simple case. So, a case of a dumbbell. Let us assume that this is RCM, which will write as RC for brief. Okay. This is the center of mass of this dumbbell, and both the masses are equal, m and m, and mass, this is the earth. So, this is earth. It can be earth or it can be any satellite, heavenly body. So, what we observe from this place, if we join this and say this is the first mass, this is the second mass, and we write this as R 1 and this is the R 2. So, obviously, you see that this distance from the center of the earth is less and this distance is more, and therefore, the force acting on this particular mass here in this direction, which is we can write as F 2, and here along this direction we can write as F 1. So, F 1 magnitude, this is greater than F 2 magnitude for this particular configuration. So, what does it imply? That at this point, which is the center of mass of this dumbbell, so there will be a torque acting like this, okay, because the torque will act in the opposite direction, because this force is more. So, this force is more. So, and here the force acting is less as compared to this one. So, there will be a net torque along this direction. So, as shown by this arrow. So, this is the net torque, and this is nothing but your gravity gradient torque, net torque, which we write as gravity gradient torque, means this torque arises because of variation in the gravity, arises because of variation in gravitational acceleration. So, this simple figure, it says how your satellite can get affected because of the gravitational pull of the earth. Now, let us say another case we take here in this place. Say we have the case of ellipsoid. Okay, this is the center of mass of the ellipsoid, and earth is somewhere here. This is your earth. This is the center of the earth. So, this is here in this situation, you can see that on this half there will be more gravitational pull as compared to this half. So, here if we indicate by F 1, on this side the force by F 2. So, obviously, F 1 is greater than F 2, and this implies that there will be a tendency for this satellite to turn like this. Okay. So, means this implies that if your satellite is in a of a shape where there is a net torque due to the gravitational force about the center of mass, then satellite will not remain in that position. And this kind of situation, though here in this case what we see from this place, that if my say here in this situation, for this case I am discussing, that initially if your satellites, these two satellites were these two halves were like this, means the dumbbell was initially in this shape, and from this you have moved it to this configuration. So, obviously, there will be a torque which will try to restore it back. Okay. So, it will try to pull it here in this direction. So, once it is disturbed from this situation, if it is disturbed from this configuration to this configuration, okay. So, there will be a net torque here in this direction, which will try to move it toward the original position. So, we call this kind of case it is a stable. Okay. It is a gravity gradient stability, means once we are discussing. So, this is simply a stable case, but it so happens that because the gravitational forces it is a conservative. So, therefore, this will keep oscillating, and you need to damp out these things until unless if there are other factors which is trying to damp it. On the other hand, if you take a case where your satellite is in the form of a dumbbell and it is looking like this, and it is in this configuration, here is your earth. Okay. So, you can observe that the forces acting on these two masses will be same because of this configuration. Okay. Now, if you disturb from this configuration, then what happens? So, once it is disturbed from this configuration and say it comes to this position after disturbance, then what will happen? You see that this force, the force acting on this and force acting on this, if this is F 1 and this is F 2. So, F 1 magnitude, this will be greater than F 2 magnitude, and what this will do? This will give it a net torque here in this direction. So, if your dumbbell which was lying like this, dumbbell satellite which is originally in this position and it is disturbed to this position. So, it will not tend to return back to the original configuration, rather it will go and it will keep moving and it will come to this position. Means for the stability earlier we have discussed that there should be tendency to return back toward the original equilibrium position. So, here this is statically not stable, it is simply it implies if we look here in this static configuration, and moreover if it is left over a period of time, it will go away from this position and it will start oscillating. Okay. So, this kind of configuration is unstable, because the disturbance it increases over a period of time. You have given initial disturbance by say this angle you have disturbed, this angle is here something like theta. So, this angle will increase over a period of time, it will not decrease. Okay, and therefore, this configuration it is a statically unstable, and dynamically what we see that here in this case we will have to do a lot more work before we finally come to whether it is a dynamically stable or not. But once we can say that if it is statically unstable, there is no restoring force, means it is a dynamically unstable. So, this thing we are going to analyze mathematically. Okay. This is a very simple representation, but for our actual satellite modeling, once we are doing it for say the ISRO is working. So, and if is designing a gravity gradient satellite. So, this whatever we have discussed till now, it is not enough. We need to discuss these things in terms of mathematics and make the things very precise, so that proper fabrication of the satellite and its how much time it will take to, say here in this case, as we are discussing this particular case, that if it is, this was the original position, okay, and this is the disturbed position. So, if it is disturbed from the original position, how far by a certain amount. So, we have disturbed it from this position to this position. Okay. So, by theta angle, let us say that we have disturbed it. So, how much time it takes to go from this position to this position? All these things you can work out, it is all possible. Okay. You can do various kind of studies, what will be the period of oscillation, because the gravitational force is conservative. So, if it is oscillating all the time, so how, what will be the period of oscillation, whether it will affect your mission, and so on, many things need to be discussed. So, with this we start with, in the main purpose, say your satellite can be in an elliptical orbit or it can be in a circular orbit. Say for this, assume that this is a circular orbit and here this is the center of the earth. Okay. And this is your satellite. So, earlier in the very first class we have discussed about the reference system. So, let us assume that this is the velocity vector of the satellite. So, along this direction we write E1 O, means this is the first or the x axis of the orbital axis. So, this is the orbital x axis. And how we have written the depicted the orbital axis, E1 along this direction and E2 along, E2 taking the right hand rule. So, it will be down and we will show it by cross. This is E2 and this O stands for the orbital, and E3 along this direction, which is pointing toward the center of the earth. So, this is your E3 direction. So, this forms a triad. Okay. If the orbit is not circular, there are cases where your satellite may not be in a circular orbit, rather than in an elliptical orbit. Let us say that I am showing a very highly elliptical orbit. So, it is a exaggerated figure. So, let us say that your satellite is lying somewhere here. Okay. And this is the center of mass of the satellite. So, we will choose E01 along this direction. This angle, it is a perpendicular, this is 90 degree, this will be 90 degree. Okay. Velocity vector will be tangent to the, your V0 will be tangent to this ellipse. Okay. Velocity vector is always tangent to the trajectory. So, V0 is here in this direction. So, E1 along this direction, this is the center of the earth, we can write this as EC, earth center, circular orbit, elliptical E2, and this we are writing as EO3, and obviously here EO2 it goes inside. So, E1, E2, E3. So, you can see that here your velocity vector is also along the same direction. This is the velocity vector. So, both are coinciding. So, from where this notation is arising, we will follow this notation. This notation arises from the aircraft. In the case of the aircraft, okay, x axis is taken along this direction, y axis like this, and z axis vertically downward toward the belly of the aircraft. And you know that aircraft it flies along this direction. So, v is along this direction. It may happen that v can be also along this direction, but the body axis it is a fixed along this direction. So, this is the body axis here in this case. We are not talking here about the body axis. This is simply the orbital axis, and with respect to this orbital axis, the E1 0, E2 0, E3 0, this is the triad, and with respect to this your body is oriented. Okay. So, here I have shown the body to be like this. So, let us say that your body is arbitrarily, I can show it like this. This is E1, E2, E3, and if we put B here. So, this indicates this is for the body axis. Similarly, here in this case I can show it, but I will not make it clumsy. So, remember that your E1 axis will be always shown like this. Here this is the orbital axis system, the orbital axis system, it is always shown like this. This direction I will show by E3, this direction going vertically down into the page by E2, and E1 along this. So, E1 has the same sense as V0. Here in this case, if you look here in this place, so you can have rotation about the velocity vector. So, here also if you look, this is the velocity vector. So, you can have, if the velocity vector is having the same direction as the x. So, you can have rotation about the velocity axis, but obviously for the aircraft the things are much more complicated. It is a representation, there are the angle of attack, side slip, and so many things are there that needs to be discussed before anything can be mentioned about the aircraft. So, we confine ourselves to the satellite and discuss further on this. So, this is the basic description. Okay. There is another notation which is called the LVLH. This is local vertical, local horizontal. If you look into the journal papers, so some of the journal papers, instead of considering E0 here in this direction, they will take E0 along this direction, okay, as shown by this arrow. So, E03 along this direction, and E02 then it will be coming out of the page. Okay. So, it will be coming out from this place. So, this particular notation we will not follow. Okay. We will follow this notation. Okay. So, let us start. So, let us assume that, say, if my E0 1 it is here, E0 2 is vertically downward, and E03. So, E1, E2, E3, E1, E2, E3, this is the right hand rule we are applying, and this points toward the center of earth. Okay. Now, this is about the what we have discussed. This is your orbital ax system. Now, what about the inertial ax system? Inertial ax system, let us say that I can fix here in this place. As you know that inertial ax system, it is a non-rotating system. So, but for describing the inertial ax system itself, it is a very complicated. Okay. If you go to the astronomy, so the axis system they use in the astronomy, it consists of 2 semester course. So, we need not go into all those details, because we have to focus on the satellite dynamics. So, what we assume that if this is the situation, I can say I can take here the inertial ax system something like this, okay, or I can have any other orientation, and with respect to this, then this system is oriented E1, E2, E3. This I can say that this is my inertial system. Already rotation we have discussed. So, with respect to this rotation is indicated. Now, going back again here in this figure, if the satellite is having velocity along this direction. So, where will be the angular velocity of the satellite? So, I will make another figure here. Let us say this is the circular orbit being shown. If we look from the top, okay. So, your angular velocity of the satellite, it will be this is called the orbital angular velocity, this which is different from orbital angular velocity. It is different from the angular velocity of the satellite with respect to this body axis. Like I have this mobile, and this mobile is rotating. So, I will say that this is the angular velocity of the satellite, it is having certain value along the 3 axis, it is having certain values, but this as a whole, this is also rotating in the orbit, it is going like this, and besides it is rotating like this. Okay. So, it is rotating like this and going all along the orbit. So, in the orbit while it moves like this, so that thing I have indicated here, this omega 0, this is also called the orbital frequency. So, the same thing also we call as the orbital frequency. So, if we want to show the angular velocity of the satellite, so this is the angular velocity with respect to the inertial ax, then how we can write? So, my satellite is rotating with respect to this axis, and this axis is rotating with respect to the inertial axis. So, your satellite is here, okay, and this satellite is, and in this direction your E, here it is your EO3. Okay. So, EO3 is changing over a period of time. After some time it will be along this direction, after some time it will be here, right now it is here. Okay. So, this will change its direction. So, with respect to this, we describe the motion of the satellite as omega r. So, omega r and plus omega 0, what this is? This is the relative angular velocity, which you call the angular velocity with respect to angular velocity of the satellite with respect to the orbital X system. while omega 0 omega 0, this is the orbital frequency or orbital angular velocity. We will not call this as the frequency, because this is a vector. So, this is orbital angular velocity. That implies, so if we vectorially add, okay, we know that angular velocity can be added. So, if we vectorially add, means this frame is rotating with angular velocity omega 0 with respect to the inertial frame. Okay. So, orbital angular velocity of the satellite, that is its center of mass is moving, okay, of the satellite center of mass with respect to the inertial axis. So, with respect to this E axis, this frame is rotating, okay, as shown here. So, as the satellite goes here, so this frame right now it is here, after some time the same thing it will come in a position so this will be E 1 0, E 2 0, and so obviously you can see that this is the center of mass of the satellite. This figure, the blue line, the rectangular part I am not showing here. So, this line, this coordinate axis, this reference axis has rotated from this place to this place. Okay. So, there is a rotation involved for the orbital axis itself. Okay. It is a very obvious, it is rotating about this vertical axis, which is passing through the page of the paper. Okay. So, this axis rotates with respect to this, and the satellite then rotates with respect to this axis. So, in this axis then we can, as we have shown the orientation here in this place like this. So, your orientation will change and it will come to some other configuration. Let us say it comes to it goes like this, E 3 comes along this direction E b, and E b 2 is here, E 1, E 2, E 3. So, this is E 2 b and here E 1 b. So, E 1, E 2, E 3, right hand rule. Okay. We are using the right hand rule, E 1, E 2 and then E 3 along the thumb. So, this orientation can change, E 1 was here. So, E 1 has gone here in this place. So, there is a rotation of the satellite with respect to the orbital axis, which is shown here by this brown line, and also there is a rotation of this orbital axis, which is shown by this brown lines with respect to the inertial axis, which I have not shown here in this place, but inertial axis, let us say that if I try to show it here, I can put it like something like this. Instead of putting it here, I am just putting it here for convenience. So, I can put it here in this place, and I can write this is E 1, this is E 2 and E 3 along this direction, okay, either E 1, E 2, E 3, whatever the way I choose to write. And therefore, from this consideration, the angular velocity of the satellite then becomes with respect to the inertial frame, it will be sum of these two. First, with the angular velocity of the orbital axis, okay, with respect to the inertial axis system, and then the orbital then the angular velocity of the satellite with respect to the orbital axis system. So, you get this very clearly that the first this rotation is referring to the this coordinate this reference axis, the orbital reference axis rotation with respect to the inertial axis system. Okay, this is your orbital axis system, orbital axis, and this is the inertial axis system. So, this is rotating with respect to this, and with respect to this, then the satellite is rotating. So, both are then vectorially added to get the net angular velocity of the satellite. Okay, so, this puts the background for discussing further rest of the things. Okay. Now, we go back we have to again discuss about the rotation and other things, but I will come to that later on. Let us start with the developments. Basic formulation for the gravity gradient satellite. If we take this to be the earth, this is the orbit, and I have a rigid body here. We are discussing with the respect to the rigid body. This is a rigid body here in this place. This figure is exaggerated, remember, because this is earth is very large. This radius is around 6374 kilometers, while your satellite may be of few meter radius. So, do not take as it is. Okay. If this is the situation, then the whole development whatever I am going to do here, it will be totally different from that. So, this is the center of mass of this satellite. We take a small mass inside this satellite and say this mass is d m, this vector we write as rho, and the vector from the center of the earth to this place we write this as r c, indicating that this is the center of mass of the satellite. This we can see set as c, and then finally, this point we can join together, and this is your r. So, the radius vector of mass m, that becomes r equal to r c plus rho. So, obviously, as we have discussed in the case of the dumbbell, there will be a force acting on this mass, okay, and we can take torque about this point, about the center of mass. So, already as per our earlier discussion in the previous lectures, that if we write the torque equation about the center of mass, then no extra term appears, but if we write about some any other point, then the extra term appears. So, therefore, we are choosing here the center of mass and not any other point. Okay. Therefore, the torque about the center of mass of the satellite can be written as rho cross d f, where d f is the force acting on the. So, d f will be along this direction. Here it will be acting along, I will show it by some other color. This is your d f, the force acting on this, and this we write as d m equal to d f. Now, this case can be very complicated. If we consider the earth to be oblate, okay, then the system, and moreover the density of the earth, it is a varying, as you know, it is not constant throughout the sphere of the earth. Okay. So, if we start discussing that way, it will be very tough to develop this topic, particularly in this class. If you are interested in looking at how the oblate earth, the acceleration due to at any point due to an oblate earth is represented. So, you can refer to the book on geodesy. This is a book on geodesy by Kaula. So, this is our basic equation, and what are the assumptions we are going to make here? We need to make certain assumptions. That is, satellite gets affected only by the primary means in this case it is earth. There is moon also, but moon consideration it cannot will not take it, and the sun is also present. So, if we are trying to do very accurate propagation of the satellite orbit, so in that case the perturbation due to the moon, sun and various other planets is taken, but for this the attitude dynamics it is not required. So, if the size of the satellite is very large, like it is a say the you are considering the moon itself, okay, which is a satellite of the earth, okay, but the distance now it becomes large, but if this distance is reduced and say the it is a moving just near the surface of the earth, size of the satellite which is of the size of the moon, then we need to consider various other factors. Okay. So, here we will simplify it as the case that this is my primary body, and about this is satellite which is moving. So, this is the first assumption. Then we will assume that as you know from the Newton's law, that the gravity due to this place, this whole earth, because the inside the density is varying, okay, and therefore, the acceleration due to gravity at this point it can be very complicated, but we will simplify this assuming that the whole mass of the earth is concentrated at this point O prime, which is the center of the earth. C is the center of the earth. So, here spherical symmetry is present. This is not oblate case. For the oblate case, this is the oblate. For the oblate case, you have to look into the book on geodesy by Kaula. So, spherical symmetry and uniform density. The spacecraft or the satellite is a rigid body. We are not discussing it for the flexible case. And the fourth, as we have discussed, that this is a very small as compared to the distance from this place to this place. So, the fourth is satellite size is much small as compared to the distance between the center of mass and the center of earth. So, under these 4 assumptions we can develop the satellite dynamics under gravity gradient. So, already we have written that d m, the torque acting on the satellite, it can be written as rho cross d f, and if we put a g here. So, this just indicates that this is the force due to the gravity. So, f g is the force due to gravity. And as we know, this d f g can be written as mu by this r magnitude whole cube, going back here in this place. So, this is your r vector is along this direction. Okay. So, magnitude of the distance from this point to this point, this is r magnitude. So, r magnitude and then the unit vector along multiplied by here d m and the unit vector here in this direction. So, because we have put here cube, so we will not write unit vector, but rather write this as r. Okay. If we write here r square, so then we will write in terms of the unit vector along the r direction. So, unit vector along this direction, okay. This is r cap, while r is a vector along this direction. Okay. Now, if we have to calculate the whole torque, so if we want m, so we must integrate this over the whole body, okay, which simply I will write this as b, or we can remove this b altogether. Okay. This is just integration over the whole body, and therefore, this becomes rho cross, and here we need to put a minus sign, because the gravitational force it is acting along this direction. It is a gravitational force is opposite to the r direction. R is here, this is your r direction, okay, while the gravitational force direction it is along here, okay, toward the center of the earth, and therefore, we must put a minus sign here in this place. Okay. And if we put that minus sign, so we can write this as mu r d m, and then okay. So, this is our basic equation, and we need to develop it further to get the equation of motion of this rigid body, which is in this case the spacecraft under gravity gradient. So, thank you very much.